Welcome to Study Loop.
Our question says that a basketball leaves a player's hand at a height of 2.1 meters above the floor. The basket is 3.05 meters above the floor. The player likes to shoot the ball at 38-degree angle. If the shot is made from a horizontal distance of 11 meters and must be accurate within plus or minus 0.22 meters because of the size of the goal, what is the range of the initial speed that is allowed in order for the player to be able to make the basket? So I wrote out here some of the things we were given initially. I wrote that the y sub, I'm going to write this as y sub p for the player. The height of the player is 2.10 meters. Y sub b, I'm going to write this as y sub b for the height of the basket is 3.05 meters. The shot of the angle is 38 degrees. X is equal to 11 meters, that's the distance away, and the accuracy of X, or the allowed uncertainty on X, I write as sigma X, is equal to plus or minus 0.22 meters. So the first thing I'm going to do is I'm going to adjust the coordinate system, and I'm going to make the initial y0 value the place where the ball leaves the player's hand. And then so the y value it travels is going to be equal to y of b, the height of the basket, minus y of p, because y of p is now going to be 0, like that, or y of p, I'm sorry, isn't 0, but I'm going to make the height of the origin point the player's hands, where y of p starts. So then the total height it travels will be y of b minus y of p, which is 0.95 meters. Okay. Now, we can use this coordinate system and the equation y is equal to y naught plus v naught of y times the time plus 1/2 acceleration in the y direction, a of y, times the time squared. Okay, and in our new coordinate system, y of 0 is the origin point, it's 0, right? So let's go ahead and simplify this. We now have y is equal to 0 plus v naught of y. Well, that is v naught times the sine of theta, okay? So the initial velocity times the sine of the angle is the velocity in the y direction. Well, v naught is what we're trying to solve for here. So we're getting to a good place where we, at least in our equation, we have v naught, and we have some things that we know, like theta, we know y, and then we also have plus 1/2 a of y. Well, a of y is gravity in the negative y direction. So this is going to actually be minus 1/2 times gravity, acceleration of gravity, times t squared. Oh, also, I forgot my t here, because this is v naught sine theta times time, of course. Get right units here, because we want units of meters, plus, or I'm sorry, we just went over this, minus, from the negative direction of gravity, minus 1/2 g of t squared. Okay. Well, v naught is what we're trying to find, but we don't know t. So we're getting to the right direction, but we don't know t. Well, how can we find t? Well, one thing we do know, we can use our distance traveled formula, where it's distance traveled is equal to v of x times the time, right? Okay, well, we know distance, so maybe we can use this then to help simplify our equation and solve for v naught. So let's rearrange. Well, we'll first realize that this is equal to v naught times the cosine of theta. So once again, we have v naught. Two equations, two unknowns. We should be able to solve this. Times the cosine of theta times the time. Now we solve for time. It's equal to x, which we know, divided by v naught sine theta, or cosine theta, since it's x. Okay, now let's plug this back into our equation, which I'm going to star here with red. Let's plug it back into this equation, and we find that y is equal to the 0, we'll just ignore that, right? V naught sine theta. Then plug in what we just found for time, which is x divided by V naught, it's a theta here, divided by V naught cosine theta minus 1/2 times the gravity times t squared. So this is going to be x over V naught cos theta. And this whole thing is squared. Okay. Well, the V naughts here are going to cancel. And we can also recognize that sine theta over cosine theta is equal to tangent theta. And let's go ahead and start to simplify this a little bit. So let's get a new page here. Starting to simplify this, try to get V naught by itself and isolate V naught, because now everything in the equation is stuff we know except for V naught. So we have x squared over V naught squared cosine squared theta is equal to, and this is -2 from the minus 1/2 times y minus x tangent theta, because remember sine theta over cosine theta is tangent theta, divided by g. So now we're going to isolate V naught, keep solving this out, find V naught. The equations are going to get inverted to get V naught in the numerator instead of the denominator. We're going to have a square root since V naught is squared. This is going to be equal to the square root of g times x squared divided by 2 times cosine squared theta times -y plus x tangent theta. So I just distributed that negative sign through there. Okay, in the parenthesis, this is all in the numerator, so let's extend that. It's all into the square root, extend that. Okay, well, we weren't just given a specific x value. We were given a range of x values that we could land it within. So we want to figure out the maximum minimum velocity to get it within the maximum and minimum allowed x values. So we'll say first x minimum, well, that's going to be equal to the x value we were given minus the uncertainty in x. So if we go back to the previous page, x is 11 meters minus the uncertainty, which is 0.22 meters. And that's going to give us 10.78 meters. Okay. So then to solve for the minimum value of V naught at this x value, we would just plug in 10.78 meters into the x squared part of V naught in the equation above, and then everything else, as well as the x part next to the tangent theta, then everything else we already given on the previous page. Theta is 38 degrees. We have g is 9.8 meters per second squared. So plug in all those values and we find a minimum, we'll call this V min of 0 is equal to, and this comes out to be 11.1 meters per second. Okay, so that's the minimum initial velocity value. Now we need to find maximum. So when x is maximum, the maximum allowed is equal to x plus the uncertainty. So this is 11 plus 0.22. If you do that, you get 11.22 meters. So now we're going to plug in 11.22 for all the x values in the V naught equation above, and we're going to find the maximum. We'll call that V max initial, M-A-X, and then initial 0. So V max 0 is equal to, plugging in all those values, using the same values for theta and for gravity, we find this is 11.3 meters per second. So that's the maximum minimum range of velocities to get it there.